each basin there's a problem that's addressed. It's called a basin development challenge. So in the Ganges, the challenge is to increase the resilience of both agricultural and aquaculture systems in the coastal zone. Why did they pick the coastal zone of the Ganges Delta? There's lots of really poor, food insecure, vulnerable people there. Population is very dense. The productivity of both land and water is extremely low. They missed out completely on the Green Revolution. Also, in phase one, there were two excellent projects under the challenge program led by Tung and Abdul, and so CPWF very sensibly thought they should build on the achievements and the networks of those two projects. Those projects showed that there's good potential to greatly increase land and water productivity of cropping systems in the coastal zone. And I believe that the coastal zone offers the potential for Bangladesh to make a quantum leap in meeting future food security requirements because the land and water is so underused. In the Ganges Basin Development Challenge, there are actually 5 projects. The projects were designed by a small committee which involved CP Tung and Manoranjan Mondal and a couple of others, and then the projects were commissioned unlike phase one. So we had a coordinated approach from several projects on a single problem. Most of them are led by CG centres, but G4 is led by the Bangladesh Institute of Water Modelling. They do really excellent work, and in this project their challenge is to get data by direct measurement and from various sources and use modelling to understand the situation about the water resources now and in the future in the coastal zone. I lead G2, which is about the development and evaluation of improved cropping systems. IRRI leads G3, which is about understanding how water is managed in the polders and which methods work well, if any. What's the secrets to success? Andy leads G1, which really brings together the findings from the other 3 projects, plus lots of data from other sources. They've constructed a very comprehensive GIS databases, and their job is to use that to identify which of the improved technologies would be best suited to which regions. Finally, World Fish leads the coordination and change project, which helps us to arrange policy dialogues, liaisons with CPWF, helps out with communication. So the CPWF Ganges set of projects builds on the past achievements of IRRI work, a lot of that together with IRRI, but also with some others in the coastal zone. It includes the Petra project, which is led by Noel Nagor, the 2 CPWF phase 1 projects of Tung and Abdul, and Manoranjan Mondal's work. When he left IRRI, he joined BRAC and developed the food security program, and we picked up some of the learnings from that also. So just like to pay tribute to Manoranjan. He's been working there for more than 20 years. He's really passionate about trying to improve the situation there. Makes me a bit passionate, sorry about that. And knows so much about the area, and it's really greatly influenced and shaped the work that we've been doing in the phase 1 project as well as in the current project. And of course, Tung, who was critical in phase 1. He led a wonderful project and achieved a lot of things. He then a major contributor to the design of the phase 2 program, and he still consults and helps in Andy's project, my project, and the overall program. We have lots of Bangladeshi partners, 11 of them all together, 6 of them government organisations, NGOs and universities. For G2, the main one is of course IRRI and also BRAC in this phase. We have a couple of partners in India, but I'm not going to talk about the work in India today. So in my project there's lots of people, this I can only just show some of the people in the team. There are some IRRI hybrids there like Rafik and Eklis and Manoranjan and many others. And everything I'm going to tell you today I've learned from all these people, and so yeah, I'm just the messenger. Okay, so the phase 2 CPWF program is focused in the coastal zone, in the southwest and south central coastal zone of Bangladesh. It's a delta, so it's a very some of them quite large, up to several kilometres wide, but it's such a dense network you can hardly see any of it in this particular photo. Our work in the coastal zone, of course, does not go into the Sundarbans, which is the world's largest mangrove forest. It's a UNESCO World Heritage Area, and there is huge biodiversity and several sanctuaries trying to protect some of that biodiversity. But the rest of the coastal zone is also a really fascinating place. I go there 2 or 3 times a year. It never ceases to be really interesting. There's so much diversity in the landscape, across the seasons. There's so much activity and different cropping systems. So I recommend it for a holiday. So the big constraints to productivity in the coastal zone are firstly too much water in the rainy season, lack of fresh water in the dry season, salinity and cyclonic events which can be extremely devastating. And these things are all going to get worse because of climate change, reduced river flows from India and sinking of the lands that are protected by the polders. The coastal zone receives about 2,000 millimetres of rain a year on average. It's a little bit variable over time and over space. There are 3 theoretical rice cropping seasons: the Alsh crop, which is planted in May, harvested in August, the almond crop, and the borrow crop. They're all 3 different rice crops, and then there's also non-rice crops, which are grown during the dry season. But in the coastal zone, nearly everywhere there is an almond crop. It's the main season crop, the rainy season crop. And in some places there's a bit of ash, in some places there's a bit of borrow, in some places there's some roti. The rivers are tidal, up to about 150 kilometres inland. These 2 photos were taken at the same location. You can see the same trees in those red rings. The first photo's at high tide, and the one on the right, it's at low tide, but the tide's actually still going down in that photo. So in the rainy season, there's tidal fluctuations of 2 to 3 metres, a bit less in the dry season. Second thing is the salinity is variable. The salinity is highest in the southwest corner, and it's highest as you get closer to the sea, but also it changes throughout the year. In the dry season, the salinity is much higher in the rainy season, and that's because there's reduced flows of water coming down the rivers, so the seawater moves further up the rivers. The soil salinity is also increasing over time, and that was the boundary in 1973, the blue line, 2000, 2009. And this is largely due to the fact that flows down the rivers are decreasing. And sea level rise will of course make that far worse. This is an example of the salinity dynamics in a moderately saline region. So here the river starts to get too saline for irrigation in mid-February, and it remains so until late June, and then the water's very fresh because there's lots of fresh water coming down the rivers. That's the situation in a moderately saline region. It's different in other places. In the south central area, there's fresh water virtually year-round because there's so much water flowing down those rivers. In the southwest corner, it's the opposite. The salinity starts a lot earlier and it gets higher and stays there for longer. So about 50 years ago, there were 139 polders constructed in the coastal zone to protect the lands from tidal flooding in the rainy season and from salinity intrusion in the dry season. And this enabled the production of a single rainy season almond rice crop. In my project, we're working in 3 polders across this coastal zone representing the different salinity regimes, from low salinity to high salinity. So we're just going to zoom in now on polders, in a moment in polder 30. Our World Fish partners in G2 did a survey of households in those 3 polders, and land holdings are very small. More than 50% of the rural households have less than 0.2 hectares, which is less than 50 metres by 40 metres, not much. And this is pretty much the same right across those different salinity regimes. So zooming in on polder 30, it's surrounded by rivers on most sides except for the southwestern side where the polder comes across the land there. And we're just going to show you some photos roughly where that red dot is. So that's the river outside the polder, and this is the dike or the embankment. It's high tide, so you can see the water level in the river. This is inside the polder. There's already about 20 centimetres of water on the land at that particular point. So you could imagine if the embankment wasn't there, those lands are unusable. They'd just be all underwater twice a day. So again, the picture at high tide, and this is showing a sluice gate in the embankment, and it's open and it's letting water into the embankment for irrigation. At the time I took that photo, some of the higher lands in the polder didn't have enough water to be able to prepare the land for rice, so they were still letting water in. This is taken at a different time, and this time it's at low tide and there's water draining out of the polder. You can see the people down there fishing in that water, and again showing you, those people are 1.5 metres tall, I suppose, so you get a feel for the height differences. So the sluice gates can be used for letting water in at high tide and letting water out at low tide. And water's sometimes let in to start the rice crop and also to finish it. So in addition to rivers around the polders, there's a very dense network of old rivers, canals, distributaries inside the polders. So most fields in polder 30 would be within 1 kilometre of one of these old canals or culls. And in this particular polder, there are 11 sluice gates in some of the larger culls connecting them to the rivers so they can let water in and out. The culls vary greatly in size. They can be used to store fresh water during the dry season, but they're often heavily silted up and some no longer even exist. So traditional rice is grown in the polders, followed by lots of fallow and sometimes in some places by a legume crop. So here's the traditional rice vine that's been transplanted in late August this year, and you can see that they're using very old seedlings. They're getting to a metre tall already. The rice is photoperiod sensitive. This means that no matter when you plant it, it's not going to start to go into the reproductive stage until the days start getting shorter, which means it's not going to be ready for harvesting until December or January. And there's an awful lot of root pruning goes on when the seedlings are pulled out, and very severe transplanting shock. So they only get 2 to 3 tons per hectare. After rice harvest, there's lots of fallow for about 6 months. In some places, there's legume crops planted, but they're planted late because of the late rice harvest, and they're often damaged by the early monsoon rains. And this year, they were destroyed by the very heavy rains in May. In this photo, the cows have been let in to graze them a little bit. And the one on the right-hand side of the bottom is the sesame, totally destroyed. Our household survey showed that 80% of the people living in those 3 polders were living below the national poverty line, which is double the national average for Bangladesh. So extremely poor people in that region. Why did the coastal zone miss out on the Green Revolution? So as you all know, the Green Revolution involved introducing high-yielding varieties, huge expansion of groundwater irrigation for a huge expansion of borrow rice and fertilisers and other inputs. The coastal zone missed out because the water is too deep for high-yielding varieties because they're shorter than the traditional varieties, and the high-yielding varieties, because the reproductive stage is delayed, then it happens after the worst flooding's over. The late harvest of the traditional varieties causes late establishment of the rabi crops, so you're very limited to what crops you can grow, and they're not going to do very well anyway. And there's a lack of fresh water for growing huge areas of borrow rice. These are some examples of too much water. This is the photo I showed you before where they're letting water in for the highlands, but at the same time, in the lowlands, there's way too much water, and here's a seedling nursery drowning, another water management issue. Here they're transplanting in August, clearly it's way too deep for high yielding varieties. And here it's too deep for any varieties. And this is in a location, it's in a low-lying area where the drainage has been blocked, the culls have been silted up, and there's a road blocking a natural drainage line. The problem of too much water for high-yielding rice can be solved. Firstly, by systematic operation of the sluice gates to let out the excess water, by separation of lands of different elevation, by strategic investments in infrastructure, and by desilting the culls. So, this is the river, here's the embankment, and here's inside the polder. At low tide, the river's down here, this is in the rainy season, and high tide, it's way up here. So, if there's too much water in the polder, we can simply open the sluice gates and let it out. This is a lovely example from one of our PhD scholars on the benefits of early drainage for almond rice. It's theory done 49, it had just been transplanted. And then 3 days later there was heavy rain and the crop was not quite submerged. You can still see it just peeking through the water there. But this field was in the lowest lying part of that area. They had a bund, but it turned out not to be big enough, and so they got completely inundated by water flowing in from elsewhere. They drained the field, but the crop's looking pretty sick, and then had about 4 days of inundation and 10 days of too much water. And then they had another inundation for 3 days. This time they got the water off quicker, and they raised their levee yet again. But the crop recovered, and they got 5.5 to 6 tonnes per hectare. So if you can drain, you can have high yields of high-yielding varieties. The other message that came through clearly there is that we need to separate lands of higher and lower elevation so that we can control water. This can be done using existing infrastructure and building some small levees where needed. This is a 6-hectare pilot community water catchment. So here's the river, here's the sluice gate and the cull coming along here. So there's roads on 3 sides, so all we had to do was build one small levee drain to make a little water management unit so we could control water. Last year there was more than 250 millimetres of rain on 2 separate occasions within a couple of days. The first time just after transplanting of the HYV, but by operation of the sluice gate they were able to get the water off the field within 3 to 4 days. So that's about community water management. The thing is, everybody has to want to do it. One farmer cannot practice improved drainage management on their own. That's one of the big challenges.